quick announcement. Tomorrow, we were planning to host up to 3 seminars from you guys. I mean, a real quick seminar, something like 15 to 20 minutes. And then if you want to present something, if you're willing to present your research, please write to us, telling us what you are willing to present. If it's based on a research paper or it's a review, I don't know. Just write to us as soon as possible, and then we can accommodate. Of course, unfortunately, we cannot have 20 seminars, so that is why we're putting an upper bound of 3 seminars. And then probably at the end of the day, right, Elia? So after the last lecture of tomorrow. So please write to us. I think it's easy to find our emails anywhere in the internet, I mean. Yeah, give please, yeah. Yeah, give all short information you can get. Yes, please. So it'll be easier for us to judge. Okay, thanks. So, we finally come to a last part of our lectures, right? And today I'm going to talk about a little bit of applications of things that we've been discussing in some specific theories. But before that, I want to address some specific features that we haven't discussed so far. So, we've been discussing the weak quantum field theories, right? So, what I did for you guys was to prove that those theories are in fact unitary. And when I say that they are unitary, I'm looking at a specific higher derivative theory, which is Lewick's, right? I'm not claiming that I gave you a proof that any higher derivative theory should be unitary in Minkowski background. I'm not saying that. Because that isn't even clear if all those theories can be unitary, as Manuel was saying earlier today. I gave you also some proofs, again, not a formal proof, but some evidences that these theories might be stable at the quantum level. At the classical level, we know that they are not. So now it's time to discuss a little bit of causality, right? Causality. As I was discussing in one of those lectures, if we take the lemma representation for the propagator, right? Not the modified one, but the usual one, which we can write in this way, right? With the spectral function in here. And let me just write here a branch cut, meaning that this integral should be evaluated along the branch cut or above the multiparticle threshold. And at large energies, right? So a very back to the envelope calculation showed to us that this thing should behave as something like this. Yes, over Q squared. And since this is positive, this integral never vanishes, right? So this lemma representation tells us that propagators must fall at most as 1 over Q squared. But we know that to those kind of theories, the propagators fall as 1 over Q to the 4th. Why I don't have a pole in here? You mean? This is the lemma representation. Okay, so if you want to take, for instance, so, for instance, you have to take this. It's outside the integral, yes. You must consider the row. You have a delta function here. Ah, okay. Now I see. So you have to be like this. 0, yeah, it can be 0 to infinity, yeah. And then you have the delta function, and then you have the extra contribution coming from loops, which comes from the thresholds. That's it. Yeah, that's it. That's it. That's it. That's it. Okay. Okay, but what really matters is this guy is never 0. And then the only guy that survives in here, this is of course a back to envelope calculation, but the only guy that survives in here is the dependence of 1 over q squared. But Lee-Wick theories, propagators fall as 1 over q to the 4th. So something must be wrong, or some of our ingredients must be broken. It's long known that at least one of these ingredients to be broken is causality, right? And I mean, just like we've been discussing, those propagators, right? In the case of Lee-Wick, which are in this form, plus a correction given by loop corrections, right? At the massive pole, right, so close to the massive ghost pole, it behaves, let's put an I here, let's put an I here. Those propagators behave just like this. And this part is associated with the imaginary part in here, right? So the fact that we have a minus sign here means that this is a ghost, as we have discussed it. So this is a ghost. But the fact that we have a minus sign in here means that causality, let's put it in this way, is reversed for this kind of propagators. And the reason is the direction of causality, or the direction of causal process in quantum mechanics or in quantum physics in general, is dictated by the I epsilons, which appear in the denominator of the Feynman propagator. And they always come with a specific sign, given by the sign that appears in the exponential in the path integral. So this minus sign here signals to us that these guys here are carrying or propagating backwards in time, but in the direction of time that we would call backwards. For them, of course, it's forward, because they are following a different arrow of causality, right? And as we discussed it before, the notion that we have of causality, it's an emergent one that is only present because you also have, I'm not writing, but you also have stable modes. And these light modes are the ones they are giving the width for this guy. So we have two features here. The fact that you have two different signs in here, two unusual minus signs, is the key feature that allows us to prove unitary. But at the same time, the minus sign here is telling us that we have violation of causality. Violations of causality at short times of order of the inverse of width. So the notion, the standard notion that we have of causality is just an emergent phenomenon, which is valid to low energies. Low energies in which you are not going to consider this propagator in this way, but you are going to Taylor expand in 1 over m squared, because the energy scales that you are working at low energies are really lower than the mass scale, so you can Taylor expand. And then you just have normal propagators plus perturbations. These perturbations you could derive in a given effective field theory. You just give you the same result. But anyway, at short times or at high energies, this guy starts to be important. If you are, for instance, close to the pole, this guy is important. So there is where you are going to have these violations of causality. So let me give you an example that was based on this paper here. Greenstein, O'Connell, and Wise. I think it's a PRD from 2007 or 2009. I think it's 2009. So the idea is the following. Let's try to do some pheno here. So if you're talking about usual normal unstable particles, you can imagine a reaction that creates this resonance at a given space-time point, and then this unstable particle propagates and then it decays in another space-time point, but which is different from the point which you have the collision which created it in the first place, and at a later time, right? Of course, if we were talking about this kind of theories, it's not in a later time, right? But in any case, these 2 points are separated. Let's say this was created, this was the collision where the unstable particle was created, and this is the point where it decays. So in any case, they are separated by 1 over gamma, which is the width of the particle. Of course, you could have considered that this gamma there for Lie-weak theories are negative, or you can just put the minus sign here and consider that the decay width is positive. It doesn't matter. What matters is this distance, right? So the idea here is to try to imagine a scattering experiment in which you scatter stable particles, right? But this scattering is made through a resonance. So the idea is to compare a normal resonance, what happens if you do the same calculation using a normal resonance, and then do the same calculation, reproduce the same calculation, but using a Lie-weak resonance. So it's kind of a Gendunk experiment to try to see how the violations of causality would emerge in a scattering experiment, right? So you can imagine, for instance, 2 initial particles. I'm writing it this way. So you can imagine 2 initial states made of 2 scalar particles. Let's just stay at the scalar level, right? So we have 2 scalar particles described by wave packets. So you can imagine that the initial state, let's put it in this way, is made in this way, for instance. You have, let's call it F, x1, F, x2. These are the wave functions associated with the particles. And let me create x1, x2, and this is the ground state, right? So I'm assuming that fx1 and fx2 are highly peaked. This is the scalar field creating the excitations in the ground state, right? Highly peaked. The Fourier transform is also highly peaked. So we would say that the Fourier transform is something like that. It's f of ki, I1 and 2, and ki, it's pi, and pi square equals mi square, for instance. So you can say that they're highly peaked, right? And then you can imagine that they are separated by a distance which is space-like. So you can put, oops, the x1, the x2, sorry. So you can say that x1 and x2 are space-like separated. And at large negative time. So they are coming from away and then they hit each other, just like an usual scattering experiment. And then you can imagine that you have some detectors placed in particular space-time points, and they can only detect particles that pass through these points, right? So we can imagine a final state wave packets in much the same way that we have written the initial ones. So the final state can also be written in a similar way, right? So you have, let's say, the final state. So we have different points, G, dx4, G, again, the wave functions, dx3, dx4, phi x3, phi x4, and these guys are highly peaked as well. Highly peaked, right? And then we can imagine again that those guys are separated by distance, described by space-like intervals. So this is also 3, 4, so this is also space-like. And again, similar to this case. So our question is, what is the probability if you, or the amplitude, probability amplitude of you starting with this initial state of ending up in this final state? So you want to calculate this amplitude of probability, right? So if you put everything together, you're going to find this. So you have an integral over everybody, right? dx1, dx2. I'm going to call dx1 prime, dx2 prime. dx1 prime, dx2 prime. It really doesn't matter, but no. Prime, just prime. So dx1, dx2, dx1 prime, dx2 prime. So we have the combinations of everybody here. So you have, so I won't forget here. So let's call it G1, G2, F1, F2, F1, F2, so we can keep track of different guys. So this comes with a star. So x1 prime minus a1 prime, d2 prime, x2 prime, I2 prime, times F1, x1 minus y1, F2, x2 minus y2, and then the combination of this guy with that one. So you see you have phi2 x2 prime, phi x2 prime, phi x1 prime, phi x2, phi x1, and the ground state. So this is a correlation function. But the fact that you started with two pairs of states, two pairs of guys in the initial and the final states, which are separated by space-like distance, the position where you put the field in here, and here, and here, here, irrelevant, right? Remember our notion of causality in quantum field theory. If you have fx1 and fx2, and these guys are space-like separated, in my convention, this is 0, right? Plus the fact that these guys here are happening at a later time in comparison with those guys. This correlation function can be put in the form of a time-ordered correlation function. So in the end, you can just insert the time order in here. fx1, fx2, sorry, 2 prime, fx1 prime, x2, 5 of x1, close, close, close. So these have a known expression in momentum space. So you would just have to write it in this way. P4, and then the guys that are leaving, P to pi to the fourth, and then the exponential, Chi1 constant 1 plus Chi2 to Chi2 minus Chi1 prime times Chi1 prime minus K2 prime times K2 prime. The delta function assuring momentum conservation. So it's K1 plus K2 minus K1 prime minus K2 prime. And then the propagators, right? So you have something that looks like this, K1 square minus my square plus I epsilon, 1 over K1 prime square minus my prime square plus I epsilon. Remember, I'm scattering stable particles, so propagator just normal. And then an amputated 4-point function, which is a function of our, I'm just going to put a big K, but it is a function of all the momenta using also the momentum conservation. Just, I was out of space here. So this guy actually had 3 components, right? So you have what we would call an S-channel contribution, an U-channel contribution, and a T-channel contribution using Mendelssohn variables. And then, since you are looking at a scattering experiment in which Z0 minus Z0 prime, it's large, the only guy here that matters is the one that is going to pass through a narrow resonance, if any, but of course, it's in this case you have a narrow resonance. That's the idea of the experiment. So these 2 guys here are not really important at large distances, but this one is, because you are passing through in the phase space of a resonance. So this will give you an appreciable contribution. Yes? Oh, you shouldn't in the way that you were constructing, but a way to separate this could be if you are willing to make the impact parameter explicit in the wave packets. You could have written here, right? You could have written here. Yes. Yes, you could. But we are not using this, right? Because, of course, if you want to analyze the whole situation, that would be important. Yeah. Yes. 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 But I want to look at only the S channel because there is the channel that the resonance will appear. Right? In these two channels, it won't appear. So, there are a bunch of calculations that we could do. I put some of them as an exercise, because I won't have time to do this calculation in full. It would take me all the time. So I'm going to skip to, let's say, the final result. So the idea is to take those guys here. You insert a delta function representation here, and you separate these two guys in two components, and then you make something that we call the stationary phase approximation to try to evaluate the integrals associated with those guys. So in the end, you can write this guy in this particular form. So this is, of course, an approximation. So a lot of steps that you have to take here, as you will see in the exercise, right? 0. So here appears the distance between the point that the resonance is creating and the point that it decays. And appears two functions here, Q, 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 G. These two functions are associated with these guys here, the propagators and the wave functions. So you collect them in these two guys here. That is basically the idea. Times the guy that we want to calculate, the amputated Green's function. So that is the information that we want to input in this formula and see what happens. So first, let us consider a normal unstable particle. So what is the Lagrangian? Well, the Lagrangian, you can write it in this way, dmi phi, similar to what we have written yesterday, minus 1 over m squared, phi squared, plus, let's say, a stable mode, which would be, let's call it chi, demi chi, minus 1 over m chi squared, plus a interaction term. So it's phi chi squared. Phi chi squared, phi square, yeah, phi square chi. So phi square chi, no. Oh, okay, no, it's phi square chi. In the notes, I think I changed it, but anyway, it doesn't really matter. So I want to look at the situation where m is bigger than m chi. So the corrections to the propagator, to the phi propagator given by the chi1 loops of chi's, we're going to produce an imaginary part for its self-energy. So it's an unstable particle, right? So its propagator can be written in the same way that we're used to. So we can use a lemma representation to write them, right? So let's use a lemma representation for it. So the propagator for the lemma representation, let's put phi. In the lemma representation, we have this ds rho s and q squared minus s outside the pole. So there is no pole here, unless you start making some conjectures about this guy. So if you take the narrow width approximation, as we saw yesterday, then this guy has this form. I call it M, right? M. So M gamma over SM square plus M square, gamma square. Again, capital gamma is the width of the particle. And because this guy has this bright Wigner shape, it is high-peaked around M square, so you can just forget about this guy here, so you can just integrate all over the real line, and then use counter integration methods. You would find that this guy has this behavior. Let's put an I here. I like to put the I's. So this is just written as 1 over Q square minus M square plus E M gamma plus, right? Now in this case, the amputated 4-point function, which I'm not going to calculate here, but you know, it's just to think about the scattering, scalar scattering of those guys. So you just take the external propagators out, and the only thing that survives is exactly the propagator associated with the unstable particle at the S channel. That is why we were interested on that. Has this form at one loop. This is a one loop calculation, right? One loop calculation. So it's a minus G squared, G, right? G, yes. And this propagator, d phi Q squared. So now you have to plug this guy into our formula to see what happens. And then again, you do it using the stationary phase approximation. Once you do the calculation, after some steps, which are just written here in my lecture notes, which I'm not going to be able to have time here, the part of the amplitude which is really important, which is not really suppressed, can be written in this form. So I'm just going to give you the whole expression. W0 is a proper time associated with the separation of these distances, right? W, 3.5. So we have F calculated in a given point. So I'm using again the stationary phase approximation, M omega, square root of omega square. So G M omega over omega square. So you have a phase, and you have exponential decay, given by exactly the decay width. So this thing is telling us that the main contribution to this overlap amplitude, it's in the first place, it only happens for a proper time which is positive, which means that the decay products appear after it was produced. That is what this theta function is telling us. And it decays. No problem, right? Now, if you do the same thing for a Lewick particle, yes, yes. Sorry, say that again. It's amputated green function, right? Yeah, you're chopping all the other propagators. You don't have, obviously, you don't have just this propagator, but you're looking just at the part that is amputated. So you're chopping the external parts.
Yeah, but it's a 4-point function, right?
Yeah. No, it's not okay. It's yeah, but it's not a bubble. It's not a bubble actually. I know what you're saying, but it's not a bubble.
I'm thinking about something like a candidate.
Yeah, but it's not just like that. It's a 4-point function at the S channel. It's not just like that. I can show you this to you later, but it's just not like that. Just not to take so much time, but I can tell you this. So let's do the same now for the Lewis case. So the Lewis case is just if we would take minus demi phi minus n1/2m square box phi square, and then the same part that is written here. So chi-field, and the interaction. The same thing. And now capital M is the largest mass scale that you have in the problem. So if you follow the same steps, right? Now in this case, it's a little bit different, right? So now you would have for instance, the modified Cayley-Lemma representation. So for the Lewis, so the phi field, let's write it this way. So you would have, for instance, q square minus mu square minus I q square minus mu square, where mu square here is m square plus I m gamma plus the part of the spectral function. Yes, rho of S for m chi square to the infinity and k square minus S plus I epsilon. So that is the form that we should use. But again, in the narrow width approximation, as we are discussing yesterday, this part here kills this part here, cancels exactly. So in the end, in practice, you only have this pole. But you always have to imagine that you have 3 structures in your propagator, right? In practice, you can just focus on this part, but you have to have in mind that if you want to write a non-perturbative expression for your propagator, you have to imagine these 3 structures. Otherwise, you're wrong. I mean, you might not be wrong, but you'll be running into problems. Let's put it this way. So if you do the same thing with this guy here, what changes in the result? You have the same form of the one-loop amputated 4-point function, right? But then, what changes are the signs? I'm not going to write again, but you have a minus sign here. In here, you have a plus sign. And in here, you have a modulus, an absolute value of this guy. So what is this Gendunk experiment is telling us? This is telling that the result of this calculation is showing that the production of the unstable particle happens at a time later than its decay. That's what is this guy is telling us. But in any case, you have an exponential decay. Because even if you have a plus sign here, the W0, the proper time, is negative. So you actually have a minus sign here. So if, and that's a big if, we could have conceived of an experimental scattering setup using Lewis particles, these calculations show us that the phenomenology would tell us this. That would be our result. Of course, you have to change the M here, right? For the M of the of the Lewis guy. Okay. So this is a phenomenological example where you can really see violations of causality, right? This is a way for you to see. So I want to brief touch a point which, of course, I will not be able to do everything here, because even if we were in a regular quantum field theory course, it would take me some time to talk about it, which is renormalization. I'm going to talk a little bit about a renormalization of this kind of higher derivative field theories, Lewis theories. But for that, I'll have to generalize a little bit our interaction terms. So why I am willing to discuss this, and why is that this could be an important point to consider? Well, one of the basic stuff that we want to calculate in renormalization are beta functions, right? Beta functions are associated with something that we call running coupling constants. And running coupling constants are a very good concept, because they allow us to treat large logarithms that would appear in our amplitudes in the case that you renormalize at a given energy scale, and then you want to apply your result at a given higher energy scale. So you would normally generate large logarithms, and the concept of running coupling constants allows you to treat correctly these large logarithms. So basically, you are interested in following logarithmic expressions such as this, where mu is this so-called subtraction point or renormalization point, etc., in using dimensional regularization, right? So for normal theories, right, two derivative theories, these are the guys that would appear at one loop. Once you are renormalizing, taking the finite part, and calculating running coupling constants. But in this kind of theories, because you have this guy here, which is an intrinsic mass scale, dimensional analysis shows us that it is possible for us to also have logs in the amplitudes which have this form. And it's okay, not a problem, but this kind of logarithms is not telling us the dependence on the energies as these guys are telling us. So when you do renormalization for this kind of theories, you have to take care of this and keep track of these contributions as well. So let me give you an example of things where if you just take the normal concepts, you could run into problems. So let us consider a scalar toy model, right? So let us consider this model, right? So Z1, demi phi minus d1 over 2m squared, box phi square. Now, Z1 squared G. No, let me write it down. Z1 squared G over 4 m to the 4. So we have dmi phi, you have dni phi, right? So this is the model that we want to study right now. So this theory has a shift symmetry, in the sense that if you take phi to minus phi, right? Or phi is a reflection symmetry as well. Phi to minus phi, or phi going to phi plus a constant, the Lagrangian stays the same, right? So shift symmetry phi to phi plus a constant and a reflection symmetry. Symmetry. So phi going to minus phi. It's easy to see, right, from this Lagrangian. All derivatives, so it's easy to see that. And all even terms, right, in phi. So despite the interactions depending on derivatives, you can prove that this theory is renormalizable. And of course, the symmetries help you to prove this. But thing is, we want to calculate one loop renormalization, so you need to calculate the vertex associated with this guy. So you do the usual calculation. For the calculation of vertex, you can just do it a simple calculation, which is just an integral of, in momentum space, of course. D1, x1, 1, 2, 3, 4. So D1, x2. Shift symmetry. Shift symmetry, yeah. Sorry, say that again. I don't think so in this case, but if you're plug in a given potential, maybe you could do that. Maybe you could do that. Mm-hmm. Yes. I'm listening. I'm listening. Mm-hmm. Mm-hmm. Yes. Yes. Mm-hmm. 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 Yes. 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 If you assume that you start with a non-trivial, yes, that agree. Yes, that agree. Yes, that, yeah, that agree. If you start with a given expectation value for phi, yes, that agree. Yes, yes, that agree. Yeah. And then you take just the usual derivatives of these fields to dx. This is just the recipe, right? To calculate vertices in Feynman rules. So this is the indirection action. So you just take this part here, do the functional derivatives, and then you find the form of the vertex in momentum space. Just do the calculation, right? So it's an easy calculation. Actually, it's not that hard. And then when you do the calculation, if you want to calculate scattering and amplitude at tree level, so let's say you are calculating this amplitude, 5 plus 5, going to 5 plus 5. So it's just this guy here, right? So it's an easy calculation. So this will produce something like this, minus ij over 2m to the 4th. Now I'm going to write everything in terms of the Mandelstam variable, s squared plus t squared plus u squared, everything. So s is p1 plus p2 squared, t, how I did it, p1 plus p3, p1 plus p3 squared, and u is just p1 plus p4 squared. That was easy, right? I mean, you take 10 minutes to do this calculation, but I won't do it in 10 minutes. I think it's an exercise in the lecture notes. If it's not an exercise, if you guys have never done this type of calculation, I would suggest for you guys to do it. But it's an easy one. So now let's go to one loop. At one loop, we have essentially in this kind of 5-4 theory, two diagrams. You have a tadpole, right? And you have a bubble. Now we have the truth propagators. This guy here is also easy to see using Feynman rules that this guy, using dimensional regularization, of course, has this form. So it's this 4. So now I haven't written, right? But the propagator is a quartic propagator, right? Putting these guys together with a Z1 as well. I didn't write it because, you know, I've been reading this since the beginning of this lecture. So it has this form, K mass, K to the 4 m square, and then the vertex. So you have a non-trivial structure in here, P square plus 2P times Q square. So this is just a standard textbook calculation, right? And then I write it again. If you do dimensional regularization, what you find, it's something like this. So you have 1 over 3 over half G over Z1. So you have 2 m's, right? M over m to the 4 P square. P, right? 1 over 4 pi square. 1 over epsilon. Epsilon is defined as 4 minus d. 4 minus d over 2, right? 4, yes, yes. I always forget the 2. Plus log of 4 pi, plus minus gamma Euler, plus a number, and the logarithm plus terms that vanish once you take epsilon to 0. So this gives you a renormalization of the tadpole, right? So that guy would enter renormalizing what we would call the wave function renormalization here, right? But it depends on p squared, not p to the 4th, so it doesn't enter here, right? So this z1, in principle, you could associate a beta function for the z1, but we won't be doing this because the log here does not depend on the p. It only depends on the mass of the ghost, right? And the subtraction point. So this is the kind of log I was telling you guys that would pop up in the calculation. So it renormalizes, of course, but it's not a contribution that, in principle, you would insert in a beta function if you want to use the standard notion of running coupling constants, right? But this is a safe calculation. Yes? That's a good question. Here, we're not using anything special. Here, you just split this up in terms of partial fractions, and you do the calculation as you do. Yes. We're not using the width here. Only if you put the width, and I'm going to do an example in a couple of minutes, then you have to take care of the contour that you are using. Because once you put the width, you have two guys with different arrows of causality. But not here. I'm not using this. So I'm just agnostic to that. I'm not studying unitarity, and so all I want to calculate is renormalization. So no problems in doing this. In the tadpole, because it doesn't have the dependence on this external momentum. In tadpole, you expect that. Oh, I'm going to show it right now. I mean, it appears, but in a different fashion. It appears. It appears. So, of course, I'm not doing the bubble calculation because it would take me, I don't know, 30 minutes to do that. Oh, I'm going to erase this part. Because it's a large calculation with a bunch of tensor integrals. You have to do Passarino-Veltman in everybody, etc. Or use standard results, which I give. I give all the recipe in the lecture notes, so you guys can have fun without me. So the bubble has this expression. So it's just 2 to 1 square. So I'm going to be careful with the factors in here. Square, square. So it's mu 4 minus d. So there is an integral of d equal q to q. So there is a numerator here. Depends on q and p. And there is this form. Well, let me write in here. Times 4 to p4. It was. This denominator, this numerator is made of the interaction vectors that I just wrote the recipe to do the calculation, right? So it's just q squared minus q to the 4th over m squared times q plus p squared minus q plus p to the 4th over m squared. And that guy is the S channel, right? So you still have U channel, and you still have T channel. And then these you have to calculate as well. But then it is easy, because you just do crossing symmetry. Once you have the S channel contribution, you can obtain the T channel or the U channel just doing some cyclic symmetry in the Mandelstam variables. It's not that difficult. The difficult part is this calculation, right? To reduce the calculation to scalar bubbles. So I'm not going to write the full expression. I wrote it in the notes, right? But there are some couple of things that we can discuss about the calculation that lies in the notes. So, for instance, let's consider two limits where the amplitude reduces, and then we can understand a little bit what's happening. So let's see the low energy limit. The low energy limit means that the mass of the ghost is large in comparison with the external momentum p. So you have logs, all kinds of logs involving p, combinations of m squared, so you just Taylor expand them. And in comparison also with the Mandelstam variables, which are just p, low energy. So at low energy, our result is a little bit easier. So you have a number here. You have what you were expecting, the tree-level amplitude, times the divergence. This is something expected. Minus g squared plus a number here. That's a big number. Again, you have a number here. Again, this guy here, st squared plus u squared, u, a log 4 pi mu squared over m squared plus a number, a big number, times s squared plus t squared plus u squared plus a number, s squared times 41 squared plus t squared plus u squared. Now that's a log, which depends on the energy, right? Now there are three terms where you do the symmetry associated with the crossing symmetry, so you just take it, oops. So I'm going to write it in this way. It's not exactly this. So just to give you a notion that the other term is a t here, 41 appear in a t and a t here. And the other one is the same for the u. Just a compact form to represent these guys. Oops, that's the large one. Then you see again g squared, right? So you have again a number. Now s to the fourth plus 2 to the fourth, u to the fourth, plus again a number, s squared, t squared, plus t squared, u squared, plus u squared, s squared, plus again a number, s cubed plus t cubed plus u cubed, right? Okay, so this is, apart from these numbers, huge numbers that I'm not writing, this is the low energy result coming directly from the amplitude that we just calculated. So we see that the result has terms proportional to the tree-level amplitude, right? The tree-level one. Tree-level. It's just s squared plus t squared plus u squared. And then everybody's multiplying g. So we can collect all those terms and generate a loop correction to g, right? So you just take this term, you take this term. This is divergence, so you have to renormalize, et cetera, et cetera. But not this one, right? This s squared and s squared, so s to the fourth. So s to the fourth, s cubed. These terms, we are going to handle them in a minute. So, okay. So now, if you collect all those terms, you will find this contribution for G, right? So G, which depends on the subtraction point. Let's call it a bare G, which appears in the Lagrangian, right? So there is a number here. I'm going to write the number. This number I'm going to write. 32 pi square m to the fourth 1 over epsilon plus Euler gamma plus the log quad pi mu square over m square plus 11 over 30. So we see, we see that there is a log in the renormalization of G. But that is not a log which depends on the energies. It's not? I don't know, I'm not taking care of this, actually. I don't know, I'm not taking care of this. I don't know. I don't know, I just don't know. I just don't know. So, let's keep going, then someone will help us in due time. So what does that mean? It means that you are going to renormalize G, but you are not going to make it as a contribution to a beta function. Because we want to make a contribution to the beta function and call it running coupling constant if the log depends on the kinematic variables, right? Which is not the case here. So at low energy, remember, we are at low energy, G doesn't run. Contrary to your usual expectations, the expectations would be calculate the beta function using this, right? And then what is the dependence on the mu squared? It's here, so you just take the derivative and you find the beta function. But this log does not keep track of the energy dependence. So this log cannot save you from large logarithms that would appear. So it doesn't make any sense to consider this as a contribution to a beta function using the concept that we know, the notion of a running coupling constant, right? In fact, since everything here, if you want to calculate observables, right, a scattering amplitude is an observable, should be independent of mu, I can choose any mu that I want. It's just a subtraction point. It's just a point where I'm putting the renormalization conditions, where I'm defining the coupling constant, or if I had a mass, I would define the mass, etc., etc. How would I measure? Right? I can put mu equals to m, and then you would kill this logarithm. Of course, this is a very brute force way to make it disappear, but in principle, there's nothing here that you can do that. Yes, yes, but it's, yeah. Yes, exactly, yes, that's also a good point. That's also a good point. You couldn't do that if it depends on the kinematic invariant. That's a very good point that Manuel just pointed out. But you also have other logs. And these logs here are connected with other running coupling constants. Because if we were working in the effective field theory limit, we would add other terms here as well. So you see, this Lagrangian only produces quadratic terms in the Mendelssohn variables. But the result appears, it's appearing in the result, dependence on the fourth power, cubic. These guys here are associated with higher order operators that would appear in case if you were working within an effective field theory approach. And these guys would have coupling constants. And these coupling constants could be associated with runnings because they would carry logs, would display kinematic dependence. So our first lesson is, at low energies, our basic coupling does not run. But what if we go to higher energies? So low energies mean here that our ghost is not a dynamical particle, it's not active. At higher energies, this ghost starts to be active. So let's write the result at high energies. So at high energies, or energies greater than the scale of the ghost, so let's, as T and U are negative, right? So it's much greater than m squared. Not that much greater, because there is another Strong-Kloppe region, which I'm not going to discuss about it, which everything in perturbation theory would collapse, in the sense that we couldn't use perturbation theory to explore the results. So I'm not in that region, right? It's a large energy, but I'm not in the region. So now I have this expression. So you have G over 2 m to the fourth. So 1 minus G, 17G, m to the fourth. Now 1 over 2 pi square, m to the fourth. S squared plus T squared plus U squared minus G squared, m to the fourth over 102 P squared, m to the fourth, m to 8. Ooh. Oh dear. Log m squared. Now that's 13 s squared plus T squared plus U squared plus the same thing that I just told you about the other calculation, right? And that's it. Now we can renormalize the coupling constant at a given renormalization point, right? We can choose this guy. You can choose any guy to do the renormalization. So So renormalize G, renormalize G at an off-shell point, S equals T equals U to square. So you have an expression for G where it's a renormalization of G, right? So it's something like it's G plus this number here, log of mu r square over m square plus a number here. So that is just a value to renormalize G. And then the amplitude, after you renormalize G, acquires this form. U r s squared plus t squared plus u squared over 2m to the fourth minus G bar squared little m to the fourth 1 over 102 pi square m to the 8 and our logarithms. Log minus s over mu r squared 13s squared plus 2 squared plus u squared plus the terms that you gain using crossing symmetry. So now our logs, our kinematic logs, right, are multiplying the dependence which appears in our Lagrangian. So we can use this G now as a running coupling constant in order to accommodate the would-be large logarithms. So now there is a well-defined notion of running coupling constant for G, different that we had in our case, right? So what is the lesson here? The lesson is, depending on the energy region that you are, you can't or can apply a notion of a running coupling constant for a basic coupling. Yeah, but if we want to study the whole amplitude, which I haven't written here in the board, then you couldn't define that. I would have to write the whole amplitude for you guys, so you just have to take my word for it. You couldn't define a running coupling constant because you wouldn't have the power law dependencies on S, T, or U, in which you could collect and compare to your Lagrangian. So a well-defined notion of a running coupling constant at all should be made far from the mass threshold. Mass threshold here is given by the mass of the ghost. So you can define a running coupling constant at energies much lower, where you could use effective field theory, normal effective field theory, or at energies much higher, where you can use our full theory to do that. But depending on the energy region, you could affirm that you can use a well-defined notion of running coupling constant for our basic coupling G or not. And that is why I was specifically telling you that we were interested in tracking energy dependence. The usual notion of coupling constant, running coupling constant, is just, well, calculate the one-loop divergences, take the residue of the pole in dimensional regularization, at one loop, of course, and then you find your result. Because in normal two-derivative theories, the mu dependence equals, usually, right, Q square dependence. Q is the external momentum. So in that case, it doesn't really matter. You didn't need to do this separation of scales in here. But once you have an intrinsic mass scale, the running coupling constants that you would define using the standard renormalization techniques and mass subtraction scheme, etc., you have to be careful. Things are a little bit more subtle than looks like, right? Mm-hmm. Mm-hmm. The thing is, in this theory, you have this guy here, which makes appear an intrinsic mass scale. So you can, in principle, conceive of a given theory with an intrinsic mass scale, and then that would happen, right? Of course, I'm not saying, because you can imagine it, non-renormalizable theories, which also have an intrinsic mass scale, but I'm not discussing this kind of theories. Because these theories, you can interpret them in terms of an effective field theory. So you wouldn't never have a quartic propagator in normal effective field theories, right? So this is a brute force example where things are not, things do not work as well as we could expect. So in this last 15, 20 minutes, or 3 hours, depending on your taste, I'm going to discuss a little bit of applications, but I'm going to be brief here. I was also willing to talk about something, but I'm not doing that right now. I'm just going to skip, which is the Lewick standard model. But you can find a lot of discussion in the notes. And then you can discuss with me afterwards if you're interested in anything else. So let's discuss a little bit of applications. One quick application that I would like to discuss is the so-called Lewick ON model. So you can envisage an ON model as a model where you have n scalars, and the theory is invariant under rotation transformations. So you take the phi field, and if you consider a phi prime field where you do a rotation, A, B, O its operator belonging to the ON group, the Lagrangian must be invariant under this transformation. So this is purely this idea, right? So a normal, let's see, a normal ON model can be written in this way. I put a cube of 4, oh, 4. I put a 4. Okay. So let's call it a normal ON model. So typically, our normal ON model, we have a Lagrangian. We could write it d mu phi I, d mu phi I minus 1 over m squared phi I minus g or lambda. I call it lambda. Lambda 0 great phi I square, right? So you typically add a field, an auxiliary field, to eliminate the quartic term. So in such a way that if you integrate it out, you find this Lagrangian as well. So introducing an auxiliary field, introducing an auxiliary field, what you're going to find? You find this Lagrangian. So it's just d mu phi I, d mu phi I minus 1 over n squared phi I. Now you have a dependence. I'm going to do this, which is rather normal in this kind of theories, because in the end, you want to do an expansion in 1 over n. This would be important if you want to study large n QCD, for instance. So this could be a kind of a toy model for large n QCD, right? Unfortunately, we won't have time to go through this, but anyway, it's a nice topic as well. It's a very interesting topic. So it's a sigma square. So we have just this kind of term here, interaction term. So sigma phi A, right? So now you can, for instance, study the one loop guy here, the one loop renormalization of this guy, which is just given by a tadpole and a bubble. How do I know this? Because this is just 5 to the fourth theory, right? So at one loop, you just have a tadpole or a bubble. Because a tadpole would renormalize the mass, because it's two fields, two external fields, two. And a bubble would renormalize this guy, because you have 1, 2, 3, 4, right? Just like our model that we just studied. So there isn't anything new that we can discuss about that, right? But you can check explicitly the notion of unitarity here. So to check unitarity, what will you do? Let's say that we are studying this scattering event, right, at one loop, right? So that means that you will have to check whether this equation, no, let me write it correctly, right? So you have K1 prime C, K2 prime D. C and D are indices that appear because of those indices. Also, you do the calculation of the vertex, right? When you do the functional integration, you do it with 2 fields or 3 fields with different vertices, right? So you do a delta, delta phi C, delta, delta phi D. So also you do the derivatives in here, you would appear C and D, or whatever letter that you call. So that is why you appears these letters in here, right? So going to Q1, A, Q1A, Q2B, star, sorry, minus I, minus I, the same thing, so it equals the sum of the states, right, of A. Since this is a one-loop calculation, here should appear 3-level amplitudes. A, K2, B, going to psi, and then there is this A star, K1 prime, C, K2 prime, D, going to psi as well. In this case, since we are willing to do an expansion on 1 over n, you can prove that if you are considering phi plus phi going to phi plus phi, your amplitude should fall as 1 over n. It's easy to see because of this guy here, because you will have a propagator of this guy. And you have to sum here, and it appears 1 over n. If you put another phi here, 1 plus phi plus phi, then there is another propagator, so that it goes as 1 over n squared, and so on and so forth. And why am I doing this? Because this is important when you are considering the optical theorem. In principle, this guy here would be multi-particle states. So it's 2 to 2, 2 to 3, 2 to 4, etc., etc., etc. But in a 1 over n expansion, the leading order term, 1 over n, is just a 2-particle phase space. So this is important for you to check unitarity in a normal ON model. So the calculation is pretty much basic. You can see in some textbooks, and papers. I put some details on the calculation in the notes, but let's move on and see how we would do for the calculation concerning the Lee-Week ON model. Now we are going to do a little bit different than what we did here. In here, we didn't use the width for the calculation of the bubbles, right? We just press on using the quartic propagator, full it, right? And start doing the calculations. If we want to be a little more careful, we would have to take the fact that we are dealing with an unstable particle, and then you have to dress its propagator. And then, of course, you have to be careful with this, right? There's a bunch of things in the literature telling you how you should take care properly of these unstable particles, especially if you are discussing about gauge unstable particles. Because if you don't do ref summation correctly, your result will violate word identities, which is a horror, right? So you have to be careful in this, which is not our case here. This is just a scalar field. We won't be dealing with these difficulties. We don't need to enter in schemes such as complex mass schemes. But in a larger class, in a larger view, we would have to take more care of this. But anyway, so our Lee-Week ON model goes like this. The ON model goes like this. So let's call it a Lagrangian. Yes. So demi phi I minus 1 over 2, the term that you are already used to, phi I box phi I minus, I'm going to introduce the lambda that I just introduced before. There is a mass term. I wrote a mass term, m0 square phi I plus lambda over 8, and phi I square. So now you can eliminate this guy here, introducing the so-called Lee-Week trick using a two-field description. And you can also add an auxiliary field to eliminate the quartic interaction. So let me skip the details. In the end, your action acquires this form. So it's just demi phi, A, sorry. So we have 1 over m square. So phi I minus phi 2ai square. You can diagonalize this term as well. I'm not going to go into it, but it's not that hard. Minus 1 over n demi phi I 2i square plus m square phi 2a minus me and half sigma. Now you have phi a minus phi 2a, phi a minus phi 2a. The tilde is the Lee-Week field, and the phi without the tilde is the normal field. And then, since you have a quartic term, it's easy to see once you expand the quartic term that you have a Lee-Week field coupled with 3 normal fields. So it can decay in the same sense that we have been studying here in 3 normal fields. The other cases were just 2 normal fields, right? So at the beginning of the multiparticle threshold, you will find 4m squared. Now you will find 9m squared, because it can decay into 3 fields. 3 normal fields, right? So you can do the same calculation as before, but now we want to see what happens if we use the full propagator for the Lewick guy. So the full propagator, let's remember, right? The full, let's call it this way, the full Lewick propagator. The normal one is just the normal one. So it's just the p square. So we have minus a, 1 over p square minus m square minus a, 1 over p square minus m square, m star square, right? We have discussed this before, 1 over a. Now something that starts 9. I just call it m, right? Yeah. Infinity, ds, rho s. I just call it p, right? P squared plus a. That is the full propagator. And the bubble. The bubble is given by expressions such as this. Let's write in the 4. I use it a k or p? I use it a p. Okay. 4. So you have p squared plus or minus plus square minus, let's say m1 square. And that's 1 over p square minus n2 square, right? And I'm writing in this general form because in here you have 4 kinds of terms, right? You have a normal field and I have a ghost field. So you have a bubble made of 2, let's say 2 phi's, 1 phi and 1 phi tilde, which is the Lewick field, and 2 of them, right? You have, let's say, a big M and a small m, and vice versa. And you have 2 phi tildes, right? So in principle, this guy and this guy will not give you a problem. The problem is this guy, right? Or, if you're considering this guy, since you are working with this full form of the propagator, you might have this guy multiplying this guy. And what is the problem? Why am I saying that there is an issue here? Well, let's go to the complex plane and see the integration of P0 to see what happens. So, where are the poles of these propagators? So let's see what happens. Let's see the issue. So consider the P0 integral. The poles. So you have 2 kinds of poles. So you have this P0 pole, which is just plus minus just p squared plus m2 square. But now, let's say I'm working in a given, frame, which is the center of mass frame, in which I kill the spatial components of my external field. So the only part that survives is the time-like part, right? Yeah, the rest frame. What did I say? Okay. Yes, this is the rest frame. Sorry, I don't remember what I say. I'm just tired. So it's just plus, so this is just p squared plus m1, right? m1 squared. So, right? I haven't made any mistake? No, it's all right. So, if we go to the complex plane, right? If we were dealing with 2 normal poles, right? For instance, if instead of the big M, there would be the small m, which is the mass of the normal field, we would find just 2 poles here, or a little bit split it up here, using the I-epsilon prescription. And the normal contour, right, the normal Feynman contour will be just something like this, right? Not a big deal. But now, you have problems, because now you can have 2 poles in here, which sound normal, right? But you can also have 2 poles in here, because you are considering not only the usual pole, but also the complex conjugate pole. Actually, the complex conjugate pole is okay. The problem is this guy, right? The problem is this guy. Yes, that's what I'm going to write. Exactly, exactly. That's where the problem is. Yeah, but if you want to rotate, if you want to do the calculation, then you would have problems. So how will you do that? As I told you yesterday, in the presence of such poles, we deform the contour to form what we call the Liouville contour in the presence of interaction. So you would write something like this, right? What it's below the pole stays below the pole. So we would write something like that. But this is not enough. It could be enough if we were just calculating things at true level. But this is not enough. And how I know that this is not enough? Because if you are in the, let's say, what we will call the physical region, which would be something like that. I have to put the absolute value because these masses are complex, right? Usually you just found Q0 is greater than 2m. But since these masses are complex, you have to write the physical region like this, right? So whenever these 2 poles coincide, any of 2 poles of this guy here, if it coincides, so for instance, if you take this guy and this guy, you won't find any problems, right? Because they are in the same quadrant. But then you have this guy and this guy. And when it happens? It can happen if you are calculating a bubble where these guys here, the masses, are complex conjugate of each other. And it's just an easy calculation. Just take this guy equals this guy, and you see that the problem is going to appear once m1 square equals m2 square star. And then what's going to happen? These poles will attract each other. And then you have the contour here. And then this pole is going to pinch the contour. It's a disaster, right? As Gaston were saying, you cannot just do the weak rotation. In this form, it seems that you can do. But then you have to look at your poles. If your poles start to pinch the contour, then you have to put an additional condition. This additional condition at one loop exists. It's called the Klopp prescription. And this acronym, it stands for Kutkowski, the cutting rules guys, Lenshoff, Olive, Polkinghorne. They published a paper right after Liouville published theirs. It's a famous paper in the late 60s called a non-analytic S-matrix. It's an interesting paper, but at that time, they were only concentrating on these guys. They didn't have this guy. Coleman, as far as I know, was the first one to point it out, the importance of this guy. So a recalculation of those results will be of most importance for those guys. But I'm not going to enter into that. I'm just going to explain the Klopp prescription, which works here. The Klopp prescription says that keep m1 square different from m2 square through all calculation. Through all calculation. If you do that, then there is no problem in doing the weak rotation, right? And then at the end of the calculation, you take m1 square equals m2 star square. So at the end, you take m1 square to m2 star square. Of course, for the bubbles that you don't have this problem, you don't need to do that. You can concentrate on the parts of the bubbles that you have this problem. But of course, you can do it if you want to keep consistency through the end. You can do it for all the bubble terms. So that is the additional prescription at one loop that you must do in this case. At two loops onward, we don't know if that works. But again, this conclusion is based on the fact that you would have just two pole-like structures, not this one. And this is very important, because as we see here from this expression, and I told you guys, I was able to call your attention for that, the contribution that gives you the imaginary part for this propagator is exactly this guy here, right? Which is to be expected, right? That's why you insert these guys here. There's a whole story using of dispersion relations that uses this kind of representations, which unfortunately I will not have time to enter into this thing, right? So you would expect, your intuition would expect that once you do this carefully using the Lewis contour and the clock prescription, when you calculate the bubbles, you only have two sources of imaginary parts. One, of course, comes from the normal phi's, and the other ones comes from the product of the normal guys with the spectral contribution and the product of the spectral contribution with itself. All those products involving these two guys cannot produce imaginary part for your bubble. That's your intuition, right? That's what your propagator is saying. And if you're careful enough using clock prescription, the Lewis prescription, etc., you can prove this explicitly, that this is true. The only guy that matters once you are just worried about imaginary parts from the amplitude is this guy, apart from the normal guy, of course. So using this prescription, you can now check unitarity in this case. The one thing that you have to be careful now is that the Lewis particle, the ghost, is unstable. So now you just won't have to consider two particle states in here, in the psi, in the sum. You also have to consider 4 particle states and 6 particle states. But there is a trick which we usually use in these resonance calculations, which is instead of considering, for instance, a 4-particle state, you can consider a 2-particle state consisting of a normal field and a Lewis field. Why is that? Well, take, for instance, what we are doing, right? Let's say you are doing this. So this is a normal field, right? So this is the propagator of the auxiliary field, which enters here, right? So there are corrections. And then the final state has a normal field and the Lewis field. But Lewis field decays into 3 guys. So it decays into 1, and then you again have the auxiliary field, and then you decay in 2 and 3. So you have 1, 2, 3, 4. A 4-particle state. But a 4-particle state, the phase space divides into 2 kinds of integrals. A 3-particle integral, and then a 2-particle integral associated with these 2 guys. Since this is the decay of the Lewis, this phase space integral will produce just a decay, right? But these guys here, the integral of these guys here, would have a propagator, and you are passing through the phase space where you hit the resonance. So now you have a 1 over gamma. And these guys cancel, and the only thing that rests here are the Lorentz invariant phase space associated with these two guys here. This is just a normal calculation which works out for the Lewis case as well. This is not just something that I made up for the Lewis case. It's just the usual case for resonances. It's the sigma. Yeah, it's sigma. Yeah, it's the sigma, which is mediating the decays and their interactions. And the 6 particle state, you can also think of 2 Lewis fields. And you sum up over the 2 Lewis fields. The calculation is the same. The idea is the same. So once you do that, and you take the imaginary part of the bubble, using all the care that you need to do, you can prove unitarity for this kind of theories at one loop. Explicitly, without using all the machinery that I told you guys yesterday on largest time equation. That case is if you want all orders proof, right? Which is interesting, of course, but in practice, it's a monster, right? This is a very good calculation, but for lower loops, right? At 1 loop, at 2 loops, but starting at 3 loops is also a monster. So you must decide which things that you want to show, right? So, unfortunately, I think I'm running terribly out of time. I would have more things to discuss, which I think I won't have time, unless if you want me to continue. I can continue. I can continue? Okay, so, Gastão is putting a cutoff. Are you hungry, guys? Are you hungry or angry, or both? Are you hungry or angry, or both? Okay, just let me. So just let me finish with something that connects with some things that Manuel is discussing with you guys. But I'm not going into many of those things that I could. But let me just say this. So let me just say this thing. Suppose we want to calculate scattering amplitudes in gravity, right? So anyone who makes these calculations in gravity knows that these things could grow and start to be a monster, right? And it's difficult to do any calculation within perturbation theory, any sensible calculation. But you don't need to do it in gravity. You can just do it in normal Young-Mills case, right? Take, for instance, scattering of 2 gluons, 2 to 2 gluons, so a 4-point scattering amplitude at 3 level, no loops, right? So you will find that, I mean, you can calculate the Feynman diagrams at the S channel, T channel, U channel. It's not so difficult. But the problem is, if you want to calculate the cross-section, which is the thing that you're really interested in, you have to square this monster. And then you have to put up a lot of effort to extract a very simple result. And then you're happy. Okay, let's try to do it 5-point amplitudes. So you see that there are many Feynman diagrams that you have to consider. But still, if you are brave enough, you can calculate with your own bare hand, perhaps with a little bit of help from Mathematica. At 6 points, you will see that you'll be running into problems. So you have to be a very good guy at numerics to do the calculation. And it's a 3 level. 8 points or 9 points, it's impossible even for a computer. But then the result, if you manage to do the result, the final result for the cross-section is so simple. It's goddamn simple. So why is that you cannot do the calculation using the first principles. So that question is answered from what we call the modern amplitude methods. So the modern amplitude methods is filling us with all those kind of new techniques that allows us to do these calculations and show us that they are actually much simpler than they would be if you're willing to use the usual language of Feynman diagrams. So there is something that we call the double copy approach. What is the double copy? The double copy approach to calculate gravitational amplitudes, right? What is the mantra here, right? The mantra is the following. Once you have calculated Young-Mills amplitudes using all those new techniques that you can use, you can just take the amplitude from Young-Mills theory and a square, and boom, you have a gravity amplitude. So that is the mantra. Gravity equals gauge theory square. So that's the mantra, right? At true level. You can, this is a proof at true level. This is a proof at true level. At one loop level, you can do the calculation and show that it is true. At two loop levels as well. And then starting at 3 to 4 loops, you don't know if that is true. But anyway, it's a conjecture, right? And if you want to do calculations in n equals 8 supergravity, you have to use this, unless otherwise you won't be able to do the calculation, right? So there are a bunch of things that this gauge theory has to obey in order for you to construct the amplitudes in this way. Of course, you have to prove this, and you prove. You prove at true level that the amplitudes that you calculate in GR can be envisaged as the square of Young-Mills amplitudes, any Young-Mills that you like. So, we've been discussing here higher derivative theories, right? And then I gave it to you guys a motivation to consider higher derivative theories, which was gravity. Right? Most specifically, quadratic gravity, right? Quadratic gravity. So just a reminder, quadratic gravity. So quadratic gravity has the Lagrangian given by, no, let's just write the action. The action is just 2 over k pi square, b for x, the Einstein-Hilbert term, plus 1 over 2 psi, plus or minus Weil square, minus 1 over 2 lambda square, r square. Of course, you can also add a cosmological constant term. You can also add a surface term. You can also add a Gauss-Bonnet term. These terms will be important if you're studying one-loop renormalization, but it's not our case here. So this is a higher derivative theory, right? Higher derivative theory. So let's pretend we want to calculate scattering amplitudes in here. So imagine, if you only have GR, the calculation is already a hell. Imagine if you were going to calculate a 3-point graviton vertex with everybody here. Trust me, I've already did this calculation. This is something that you don't want to do. Trust me. A bunch of terms, a bunch of indices, it's a horror movie. But now with this double copy thing, maybe things are more interesting, right? Maybe now things are doable. So let's pretend we want to calculate scattering amplitude from quadratic gravity, coupled with matter if you want, right? You can with an action of matter, etc. You can calculate Compton amplitudes if you want. But I want to use double copy. Great. It improves, it streamlines our calculations. The thing is, which is the gauge theory? GR, we know. It's just Young-Mills. But what about quadratic gravity? Which is the gauge theory that you should use? Well, we know. And this gauge theory is known as DF-square theory. Actually, DF-square theory was created, let's put it this way, it was discovered in order to describe a kind of conformal supergravity amplitudes that Nathan and Big Ed discovered once they were studying n=4 twistor string theory. So there is a sector of n=4 twistor string theory, never mind which sector it is, but the amplitudes of this sector are described by n=4 superconformal, what is known as Berkovits-Witten theory. So they gave some amplitudes at that time, but a brute force calculation. So one way to obtain these kind of theories is to use the double copy prescription. With this gauge theory, I'm going to write it now. So this is the DF-square theory. DF-square theory. So the DF-square theory has this Lagrangian. So you have 1 over S. So this is a gauge covariant derivative mu a square minus g 1 over 3 f cubed plus. Now you have an auxiliary scalar field, a weird auxiliary scalar field, but anyway. Then you have a bunch of interactions in here. E2, C of AB, phi A, phi A mu nu, phi A mu nu, phi B, phi B, phi B, FB, plus G6, D of beta gamma, phi alpha, phi beta, phi gamma. So the gluons in this theory transform the joint representation of the gauge group. This weird scalar transforms in a given real representation, which has symmetric generators, which I'm not going to write here, but you can think then as appearing in the tensor product of a joint or in the joint representation. And then you can use in some group theory to understand these guys here. They're just a bunch of a product and symmetric product of the structure constants of the theory, right? And the relations are important because your theory, your gauge theory, must obey some relations in order for you to construct the double copy. Oh, yeah. Oh, no, the trace I've already done, right? A, B, A, B. How do I construct what? Sorry? Oh, the F cube. F cube is something like that. F cube, it's F, A, B, C, F, mu, nu, alpha, etc., etc. But there is this guy. You have to consider this guy, of course. I mean, you start from this guy, and then you see that your amplitudes are vanishing. So you have to add more information. This is in D=6 counting, it's a dimension 6 operator. So the other dimension 6 operator that you can add is this guy. Then you start with this guy and this guy, but you see that your gauge theory amplitudes do not obey the relations in order for you to construct the gravity amplitudes using double copy. So when you see that the offending terms, some offending terms need to be canceled, this cancellation is given by these scalar fields and this coupling of the scalar fields. So the scalar fields appear because you put this term here. So we can prove that these amplitudes, at least at 8 points at true level, using the double copy approach, is able to reproduce the amplitudes that Nathan and Big Ed had calculated almost 20 years ago. But what about us? What about our story? I told about the quadratic gravity. I was not talking about this, right? Well, quadratic gravity you can see as a sector of a mass deformed this guy here. So you add a mass term here. A. Now to describe quadratic gravity amplitudes at tree level, you eliminate all other terms. Eliminate this, eliminate this. So the only terms that survive are this and this. And then you call the mass deformed minimal dF square theory. So this is the gauge theory that we were after to reproduce quadratic gravity amplitudes. So the double copy here would be the mantra, right? The mantra would be quadratic gravity equals not dF square theory, square. It's dF square theory plus a spontaneously broken Young-Mills theory. Why spontaneously broken? Because in here you have a massive spin to ghost. So in order to produce a massive spin to ghost in the double copy, you have to have two massive spin 1 particles. At the dF square theory, you know you will reproduce. It's a ghost, right? But at the Young-Mills side, you don't have a consistent massive spin 1 particle unless you spontaneously broke the symmetry. So you have to consider a spontaneously broken Young-Mills. Of course, this is just the beginning of the story, right? There is also a possibility that you can supersymmetrize the dF square theory, take the double copy of each other, so SUSY dF square, to describe superconformal gravity as well. But that's an ongoing story, so I cannot just give you any details just yet. So stay tuned, I think. I'm through. Finally, I'm through. Mm-hmm. In this? Yes. Yes. You can do, yes, yes, yes. Yes, you can do it. Yeah. You have Henrik's papers and my paper. Just look for our names, Henrik Johansson and me. And in the future, both of us. So. And Fei Tang as well. Fei is also in the paper. And Thales as well. Thales Azevedo is a professor at UFRRJ. This is also not something that I mentioned, but you can also use this series to construct amplitudes in bosonic and heterotic string theories as well, using double copy. So this is a must, guys. This is a must.
How do you analyze the counting of the degrees of freedom from the gravity and the gauge?
That's a very good question, because usually here, right? Usually, you have, let's say we are in 4 dimensions, right? So the gluon has 2 degrees of freedom, right? Plus and minus. So to do a square, last time I checked, at least 2 times 2 equals 4, right? But gravity also has just 2 degrees of freedom, right? So what are those things that you were constructing? Well, from the point of view of string theory, the other stuff is expected. At low energies, you can prove that string theory not only forms GR, the Einstein-Hilbert term, but also other things, such as a dilaton, a Calbi-Ramon field, which is a two-form field. And then, from the perspective of the double copy, which in string theory has the name of KLT relations, called Weyl tie, these other fields come from the cross terms in here. So you have a plus, and minus. So plus, plus, minus, minus from the graviton. But the plus, minus, and minus, plus form the dilaton or the Calbi-Ramon. So you have to be careful if you want to describe GR, right? In practice, what you do, you correlate the helicity, right? So for instance, suppose that you want to describe this kind of amplitude. Let's put in a graviton here, let's put another graviton here, and let's say, no, let's just put in a graviton everybody, right? So, okay, this is 0, but this is not 0. This is not 0, right? So if you want to describe this amplitude using double copy, you have here a bunch of terms which depend on the momenta, right? So now here, to correlate means that 1, 2, 3, 4. 1, 2, 3, 4. So if it's a plus here, this should be a plus to form 1 plus plus. And the same for the 2, and the same for the 3, and the same for the 4. In case you put 1 plus and 1 minus, you would form 1 plus minus. It's not a graviton. It's okay, it's in your spectrum, but if you want to describe GR amplitudes, it's not in GR. Of course, this works easily in this way if you are in 4 dimensions. At true level, if you want to calculate loop contributions, if you want to go to higher dimensions, then you have to be careful. You have to insert within the amplitude something that we call state projectors. So in the case of quadratic gravity, you have to do something similar. For a massive spin-2 particle, now you have 5 degrees of freedom, right? And it will be described as a completely symmetric guy, right? So let's say that you want these 2 guys here to be our massive ghost. So let's call it massive here, massive here. So the idea is to take these 2 guys here, so ghost, 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 ghost. This would be the massive spin 1 here, right? The massive spin 1 here. And you can write it in terms of tensors. And then the idea is take these guys here and completely symmetrize the polarizations associated with those guys. Once you completely symmetrize these guys, you will be producing the spin-2 ghost in the quadratic gravity sector. So that is how you count. But again, you will produce a massive dilaton, you will produce a massive Calbi-Ramon using this map here, right? Yes, you have to subtract the dilaton if you just want to calculate quadratic gravity amplitudes, yes. Or just GR if you just know economical and you just want to do this calculation, yeah. Of course. Speak louder, man. Mm-hmm. 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 At you say specifically about Gribov copies, for instance. Describe what? Sorry. Confinement. The problem is not only Gribov copies, but confinement are non-perturbative features, right? And everything here is just good old perturbation theory, you know? I just don't know how we would extract this information. I mean, there is, okay, I can, okay, there is a way to describe Wilson loops using scattering amplitudes. There is a way, which I'm not going into because it's long, it's long. But there is a way to discuss scattering Wilson loops using all these calculations from scattering amplitudes. Maybe from this side, just maybe, you could address the confinement problem. But it's definitely not clear for me. And it's definitely not clear using this stuff. Because, you know, it's in the end, it's a non-perturbative thing. So it's difficult to beat a lattice results concerning this. Well, who knows? I don't. Thank you, thank you, thank you, thank you. Don't forget, email us if you want to present a seminar tomorrow.